I guess I'll just start then. Thank you all for showing up. I realize in retrospect that the title of the workshop didn't sound that inviting, but I think I'll be able to make something interesting out of it, due to the fact that in JavaScript we have the habit of inventing everything in 7 different ways. So module systems are they have an interesting history and a lot of aspects to look at that we'll be going through today. I'll structure the workshop basically along this history. We'll start with the very simple, very broken model that we had at the start of, say, 2005, and continue to the hugely complicated but more or less working system that we're using today. The workshop will alternate between me talking and you working on some exercises. So I guess everyone has the virtual appliance with the Git repository. I did some patches yesterday, so if you didn't do a Git pull yet and you have a working Wi-Fi, it might be good to do another pull to get some last-minute updates. During the, I think we're a small enough group that it's okay to interrupt me with questions just at any time. And during the exercises, both me and Borna there will be able to help you if you get stuck or you have a question or you get confused about something. All right, so many languages, when they are designed, they come with an actual built-in module system. Not really so with JavaScript, which is both a blessing and a curse. So some languages start with a really broken module system, like C or C++, and then they just get stuck with that their entire lifetime. That didn't happen with JavaScript. Instead of that, we got everyone inventing their own module system because this is a need that people have, but the initial language didn't fill, which landed us in a bit of a mess right now. But yeah, it's a workable mess as long as you understand how it works. So we'll just be going over that. So what is the point of modules? For a long time I maintained one library that I built just as one single JavaScript file, which grew from 1,000 to 8,000 lines over the years. And there's something to be said for this. It's like it removes a lot of friction. You never have to think, where does this go? Where do I draw the boundary? What should I name this file? Stuff like that. On the other hand, people who were using this library definitely were treating it as a module. So you have that. To be able to reuse code, you'll want to be able to treat third-party code as independent modules that you just add into your project without like copy-pasting the whole file into your own file. Not only that, I also found when I finally came around to splitting this library into actual, like, relatively clean small modules, that if you build something as a single blob, even though, of course, I did apply some relatively serious abstraction and engineering practices, you just get dependencies everywhere. Everything starts to touch everything else, and it becomes really hard to create like a structure for this system. So modules also help us architect things in a way that is structured and approachable. If you come to a project that you don't know and the only file is the 8,000 file blob, the 8,000 line blob, you don't know where to start. Whereas if you have like a bunch of different files with descriptive names, you might know, okay, I'm interested in this, so I'm going to be reading that file, and it probably uses the other files in a relatively well-defined way, so I know what touches what, and everything won't be touching the whole system. that then so if we use this, if we go through history, let's start in 2007, which is about the time where JavaScript development in the large became a real thing. In 2007, there was basically very few conventions on what JavaScript modules look like, but one thing that was done a lot was just a module would define a single global and put its whole interface in that global. And if you created a project, you would add a bunch of script tags, which would load your different modules by hand. And they would all be touching the global scope. So you'd have to work out yourself the order in which you created the script tags and which ones you would need for your project. But because very people were even using or writing libraries, this wasn't that bad yet. Also, libraries rarely had their own dependencies. So if you just included a library, you were done. You didn't have to first look, okay, what does this library depend on? What does that depend on? And so on. So you'd write your script tags, and all the modules would define their global and read the globals that the other libraries defined. And if you were lucky, things would work at that point. That, of course, has some problems, which we'll get to later. Throughout this workshop, we'll use an example app, which is a very simple arithmetic exercise solving app, which I'll show here. So you, oh no. Does it show? Yeah. So it just shows you a cursor and an exercise, and then you type the answer, which in this case would be 5, and it says OK. And if you type the wrong answer, it says it's not OK, and that's all it does. Which I've split up into... this is a bit bad. Let me see if I can get it. Yeah. So there's paper.js, which defines this little thing where where you can input and output text. There's exercise.js, which uses random numbers to generate simple arithmetic exercises, and there's app.js, which ties this together into this trivial app that you're seeing. So the first set of exercises in the 2007 directory is asking you to add a dependency to this app and fix the problems that come up with that. So each exercise is under a directory using the year. So in this case, 2007. It has a readme.md, which describes the exercise. And it has a solution subdirectory, which contains the whole solution. We'll work through the solution after you've had a moment to work on the exercise. So again, so all the files that are needed for the exercise are in this directory. So if you open 2007 in a web browser, you'll get this app. And now you go ahead and break it and fix it again as you work through the exercise. And I'll give you, say, 10 minutes. The exercises get more complicated at the end, or maybe you'll just breeze through them in 5 minutes. That's also okay. If at any time you have a question or you get stuck, just talk to Borna or me. So yeah, that's a good idea. I think I have that on us. Yeah, if you don't have the virtual appliance, just clone this GitHub repository and you have all the files you need. As long as you have npm and node installed, you don't need anything else. So the first exercise asks for you to add a dependency to the project, which then ends up writing a global, which the project also used, which broke the code. So, namely the $sign function, which is a very thought-after function name. The solution, the simplest solution would be to rename your existing the existing function in exercises.js. The more general solution would be to wrap everything in an immediately invoked function expression. So you have like an anonymous function that you immediately call so that your function scope acts as a module scope and you don't use global variables for things that don't need to be global. Who got to the end of exercise 1, just to get a general impression? All right. The second exercise is about actually automatically determining dependencies. So this style of modules does not explicitly declare what it's depending on. It just happens to use a global that happens to be defined by some module who knows where it came from. I know I skipped 2 actually. The second one asks you to bundle these files, which you can do with the Unix utility cat, for example. If you just put them all after each other in one big file, they still work because they're just JavaScript programs that don't need any extra facilities. So bundling in this period was just concatenating, which was practical in a way. Then the third exercise asks for a way to actually automatically determine a dependency tree from these files, but they don't have that information yet. So the proposal in the exercise is to add a special comment format which declares this file depends on this file, and then write a little tool that matches these commands and creates a dependency graph of your project in order to automatically build these, even if you add dependencies or change dependencies, so that you are no longer responsible for manually maintaining the order of script tags that pull in your code. My solution looked like this. Does it fit on the page? Yeah. So you have a command syntax like this. It says I depend on foo.js in the same directory, so that it doesn't actually duplicate dependencies. It keeps track of the files it already visited here in this object. And then you have a function visit, which starts by saying, okay, if I already visited this, I'm done with this file. Otherwise it marks it as visited. Then it reads the whole file's content from disk, matches this kind of command, and every time it finds a command like that, it takes the file name in the command, resolves it relative to the current file so that it gets the actual absolute path to the file it's dependent on, and then recursively calls visit on that. And after it has visited all the dependencies of this file, it spits out the actual content of the file to the standard output, so that the result of running this tool is your files in the order of like sorted by the ones that don't depend on anything come first, then come the ones that depend on the ones that came first, and so on, so that when a file executes, all its dependencies have already been executed. So that works, but yeah, we'll see better ways to do this in a moment. Any questions about these exercises? Then back to the slides, I guess. Yeah, I like the little pink dots at the bottom of the projector. Okay, so what this little tool did, in effect, is building a dependency tree. And dependency trees are a very useful and important concept in like module systems and module loaders and bundlers. They kind of organize your code with relationships of who depends on who. So in this case, app dependent on paper and examples, and paper in turn dependent on jQuery. As these trees get more than one level deep, it becomes very painful to manage them by hand because you have to worry about every time you pull in a library, you have to worry about what that depends on, and you just don't want to do that anymore. We've stopped doing that a long time ago, in most environments. The main thing we want is for tools to be aware of our dependency tree, which is why explicitly declared dependencies are extremely useful. Well, the first thing we ran into in the exercises was that everything in the global scope is really not a good idea, especially if if there's not one person writing all the code, then it becomes really hard to manage who controls which global. So moving to function scope per module and only exporting one global is one step in the right direction, but of course it would be nice if we could just get rid of this global namespace entirely. That allows, for example, multiple versions of the same library to be loaded. That completely removes the danger of different libraries using the same global name, and because everyone likes cute short names and ending up conflicting with each other in that way. So in 2009, Node was announced, and it used a module system called CommonJS. CommonJS was actually a slightly bigger set of specifications, but I don't think any of that caught on, only the module system that it defined, which uses a form of explicitly declared dependencies and also completely cuts out the global scope, basically. You could call require with a module specifier, and it would return the interface to your module. So your modules basically only have access to the modules that they explicitly require, and there's no implicit magic through the global scope going on, which means that tools can pretty much read this and figure out what depends on what. It also introduces the concept of interfaces as values. So each module is allowed to set something on module.exports, which is the thing that modules that depend on them get access to. Some of them just put a single function in there. Some of them will put an object with different names for different pieces of functionality. That's pretty much what CommonJS did. One important thing is also that it introduces a resolution step. The thing you require, in my example, I'm using a relative path, but you could also use just a name, at which case the module loader was responsible for somehow resolving that to some file, which allows all kinds of intelligence and indirection to be inserted at that point, which we'll see later is extremely useful. What CommonJS does, it's like a very simple trick actually, is just wrap every module in a function which looks a lot like this. All the local things that only the module has access to are just arguments to this function. And this function's scope is going to be the module's local scope. So CommonJS modules don't run in the global scope, they run in their own scope. But that scope isn't anything new, it's just a normal function scope under the covers tricked in. If you actually create a JavaScript file with a syntax error on the first line and run it in Node, you'll see this wrapper in your error message because they don't even hide it. They just put this code around it before they evaluate your module. Our next exercise is going to be to implement a module loader which uses CommonJS. The exercise will try to kind of build that up. Let me just open the README and go through it. So in the 2009 directory, you have a bunch of scripts under tests, which are like very simple CommonJS usage. They include the .js extension and only use relative paths, so there's no clever resolution needed to to actually implement this. And your loader is expected to take a main file, read that code as a string, and then perform this thing with the wrapper around it, providing these values that a CommonJS module expects. So the first one is, well, we actually ignore file name and dir name. Those are like ways for files to notice where on the file system they live. We don't need that here. The first one is exports. When a CommonJS module is initialized, it gets a default exports object, which is just an empty object that it's allowed to add exports to. It's also allowed to override modules.exports, which is initialized to the same value, but which you can use to export, say, a function or just a single value. And the more interesting parameter is the second one, require, which is this function which resolves the string it is given relative to the current module name. So require knows which module is being run. So each module gets its own require, which knows about the module's path. And then does the same thing again, wrapping the text from that module in a function, running it, and then returning its exported value. Does that sound like a reasonable exercise, or is it going to be something that we... maybe we do 5 minutes and then we walk through it together, or what do you think? Okay, I'll start the 5 minutes. So I'll try to open the solution. The structure of this is somewhat similar to the bundler from the last exercise. It also needs to track which files it already loaded, because when you load a file multiple times in Node, it just returns the interface from the already loaded file. It just doesn't re-evaluate the module. And it also needs to like recursively go through all the modules satisfying dependencies. But the actual going into a dependency is now done by the module's code itself. It calls require. The loader does not actively go search for requires. It just waits for the module to call require. This module data structure that's passed to each module as it is loaded can be very simple. It just needs an export property, and in this case I also put a path property in it so that require can access that when it needs to resolve a relative path. Here's a function require for, which creates a require function for a given module. So that's a function which starts by resolving. Again, we only support relative paths in this simplified version of CommonJS, so it just resolves the module name relative to the current module's path. If that's already, if that's not loaded yet, it loads it, and then it returns the interface that we have for this module, because at that point it has to be loaded. I think loaded contains module objects, so yeah, it's just a map from absolute path names to module objects. And the actual module loading code uses Node's file system access read file sync to load the code for this module. Creates a module object to pass it, and then uses new function, which is like a form of evaluating, to create the function wrapper for this module. So it gets 3 arguments, exports, require, and module. These are passed to new function along with the module body, creating a function value, which is then called with the appropriate export object, require function, and module object. And then this module itself just exports a require for the current working directory, so that If you call that with some relative path, it'll resolve it relative to the working directory and load that module. Are there any questions about this code? Yeah. Right. So exercise 2 or 3, let me see which one. Exercise 2 goes into shared and cyclic dependencies. So cyclic just means that two modules depend on the same thing, which is why we had this loaded cache so that we can keep returning the same object instead of re-evaluating the module. More tricky is cyclic dependencies. So in the test directory, there's two modules, even and odd, which imported each other. CommonJS allows this under certain circumstances. Cyclic dependencies are tricky because getting the loading order right for a cyclic dependency is, like, by definition impossible, so you have to kind of hack around that. CommonJS allows cyclic dependencies if these modules don't look into the export object exported by the other before both have had a chance to load. And if they only export like this default exports object that they got, rather than defining a new exports. And that works because if you look back at the code, we start, before a module is loaded, we start by allocating a module object which creates this empty exports object. And then we immediately store that object in the is this even it's in the loaded data structure. So before an object is loaded, its default exports object is already accessible to other modules. If someone else now ends up, before this module finishes loading, ends up requiring this module, it'll get the default exports because we could create that before the module started running. And we put it into our cache so that it can be found. That way, if you write modules like this, you just require another module, and if you were to do this here, immediately read from this object. The object is still empty by the time you get it if it's a cyclic dependency, so that doesn't work. If you just take the object and only dereference it later, here in a function, which is called at some other time, that works. So this is a total hack, and you probably shouldn't use it because nicely structured module trees usually aren't cyclic. But it's occasionally useful, and this loader, by making sure that it stores a module in the cache before it evaluates it, makes that work. Any questions about that? Okay. So yeah, CommonJS works very well in the Node world. But if you have a browser, it's kind of difficult to make work because this read file sync function that we were using, it doesn't exist in the browser. You can kind of do read file by doing an HTTP request. And you can make those synchronous, but you usually really don't want to because it blocks the whole page as long as the request is running. So you'd kind of want things to be asynchronous, which CommonJS modules are fundamentally unsuited for, because if you call require, you immediately get back the interface. So require has to block your script until it has actually loaded and resolved and evaluated your dependency. That's why people came up with another module system called AMD, Asynchronous Module Definition, which roughly looks like this. You call define when you define your module. So most modules will just be one call to define with the whole module text inside of the function wrapper, which you first give an array of dependencies and then a function which takes one parameter for each of these dependencies. Then this loader library, so you need to load an actual library, require.js is a very well-known one, will first resolve and load all your dependencies, evaluate them, and only then call your module function with the actual interfaces to your dependencies. So in this case, the module is just one line which exports a function called paper. And that is the return value from this function is the interface that other modules that depend on this one get access to. So that kind of works. It allows you to run code in the browser without a build step. Of course, it still suffers from problems like if you have a big project, you'll be loading hundreds of files and it'll not be very fast. But at this point, people were still really happy to not have a build step, which is absolutely understandable because build steps do cause problems. And this was used quite a bit in the wild. I think it's going extinct just about now, but it was a big thing for a while. So now we have three systems already. First, just using plain code accessing globals, then CommonJS modules, and then AMD modules. And these are not compatible at all. So that definitely complicates the story if you want to use a library. You have to figure out how is it written, how can I consume it, somehow wire things together, which is why this beauty was invented. It's called the universal module definition. So the universal part is kind of setting it up for failure. Like it's the module definition for three different module systems that happen to be in use at the time. But this is a really ugly blob of code which feature detects module systems and then tries to use the right one, which is doable because these are kind of similar in their general structure. They define some dependencies and export a value as an interface. So in this case, the stuff at the bottom is the actual module, which is only one line here, again returning its interface. And if it's so the first if detects CommonJS style. If that happens, it assigns module.export to calling the module with the dependencies wrapped in require. So it first calls require to get the dependencies and then feeds them into the module and sets that to module.exports. If it's an AMD system, which requires the define function to be present and to have an AMD property, then it uses that format, and otherwise it just sets a global and calls the module by reading the dependencies also from globals. And this is still kind of the expected way to distribute web libraries. It's also quite an embarrassment really to our workflow, but it works, and that I guess is the important part. And you'll see most libraries, even on NPM, wrapping their stuff in something like this if they're intended mostly for the browser. It is a pain to maintain. If you add a dependency, you have to add it 3 times and easy to get wrong. It's also like it leaves traces. Even if you push your code through a fancy bundler, if you inspect the bundle, you'll still see this stuff in there multiple times because you're usually using multiple modules. It's not great, but it's like served us relatively well for a while. Then in 2010, I think, we got NPM, which is a module managing and central managing tool and a central repository for Node modules. So initially it was strictly Node. You'd get only code on there which was written for Node and not for the browser. But more and more people are seeing how easy it is to write code that works both on Node and on the browser, and even distributing browser-specific modules through NPM because it's just a really convenient way to distribute and get code. The most important thing NPM gave us is a set of conventions of what a module looks like. So before you'd have to search the web for something and then maybe find a download link to a zip or a Git repository or whatever. And then try to find the documentation, figure out what module system this thing was using. And then most people wouldn't even bother upgrading, because how would you even know that the new version was out? NPM tells us that a package has the following properties. It has a unique name by which it's registered in the repository. It has a package.json file which defines a lot of useful metadata about the package. It has a README file which is the documentation, or at least points at the documentation. It uses CommonJS, possibly more, using universal module loader, shims and stuff like that. But at least CommonJS, so you know how you can approach it. You can download it from the npm repository, and it accesses its sub-dependencies using require and then just a name, which nodes resolution, or your bundler's resolution algorithm can then map to the actual dependencies that were installed by the tool. Package.json tells you exactly the dependencies that a given package has. If it has it tells you where the main module is. If it has command line tools, it lists those so that you can easily access those. It specifies how to build and test and install the module, and it contains a bunch of more, like who's the author, where's the repository. This is all light year jump ahead from the old situation, because now we have a central agreement on what packages are, how to distribute them, and we just need to do a lot less work and a lot less figuring out to install dependencies, to manage dependencies. And of course there's npm, the command line tool, which is also useful, but completely secondary to the convention of what modules are and the central repository. It's also, there's a competing tool, Yarn, now, which is also really great. But this helps you install your dependencies in a way that allow Node to find them when you require them. It helps you upgrading dependencies, publishing your own modules to the repository, things like that. And it has been coming bundled with Node for ages now. So the question is, how does this help us run things in the browser if they're all CommonJS modules on there? We wrote a tiny bundler before, and bundlers have been kind of the community's answer to that. CommonJS can be bundled. It's a bit of a hack, because in fact CommonJS allows you to pass anything, any complicated computed expression to require. So statically determining what is being required is not theoretically possible, but because most people actually just put a string in there, it is practically possible. And you can just run a tool on your code which looks for require calls, resolves them, and just does what our bundler did before. Take all the dependencies of your dependencies, put them all in one big file, and allow you to just load one file in your web app, which is faster and easier than loading 100 separate ones. It does need to do more than our trivial bundler did before, because it also has to make sure that require returns the actual interface to the thing that's being required. So there's some more wiring going on there. The first tool that did this well was Browserify. It's still popular. It also comes with a bunch of shims for emulating Node's built-in libraries in the browser. It was really meant to allow you to run Node code in the browser, which is not necessarily a good idea. You can emulate a file system using local storage, but you probably don't want to. Though for some things, like the crypto library is quite useful, or the path library is quite useful to be able to run simple path manipulation code in the browser. So bundler is kind of just a function from a dependency tree to a single file that runs on its own. This is what required that the bundler will not be able to handle looks like. And the next exercise is, of course, to implement a bundler. The exercise is a bit more hand-holding, like it builds stuff up piece by piece. So I'm just going to say, take another 10 minutes, but first I want to explain a good strategy for this wiring up require calls with dependencies. So the thing that I found was the easiest is to rewrite the require calls. You end up creating, putting all the files that are part of your bundle into an array, which is the thing at the bottom here. These are little CommonJS modules wrapped in functions, which just end up as functions in the bundle. And they all have an index into this array, and as you process the code, you replace each, like the content of a require call, which is some kind of string or, a string. That's the only thing we support in this bundle, with an integer pointing at the index into our array of modules. So that at runtime, this very simple little runtime library that's at the top of this file can just easily figure out, okay, file number 4 is being required, so I look, did I already load that? If I didn't, I pick it out from this array of modules that has been passed as argument. They're outside of this function because they don't need to be wrapped in this scope. They could in fact break if they were wrapped into a scope that has extra variables, because they might be using those variables for something else. Which is why they're in an argument outside of our little library function. So if it hasn't been loaded yet, it's just called by with a quickly created module object, and because there's no more relative resolution going on at this point, a single require function is enough for all modules, because they all just require from this this array of bundled modules. The exercises ask you to first write a utility that scans a file for things that look like require calls with a string literal. Next, write a utility that, given a bunch of patches, updates a piece of code, and then combine these into an actual bundler. So I'm going to say 15 minutes, and I'd like to really ask you to ask for help if you get stuck. Because so far I didn't have anything to do while people were working on exercises, so definitely ask me. I have all the time in the world. So for the first one, where you need a function that processes a source file and finds all require calls, the easiest way I found to do that was to use a regex, but as I just found out, using the horribleness that is JavaScript regex is also not natural to everyone. So one way to do this is to declare a regular expression with the global flag on, which means that it'll be keeping an index into the string every time it matches, and if you call it again with exec, it'll start matching from the last match, which is a very subtle and obscure feature, but which can be really useful if you want to find all matches of a certain expression and get like full match objects with index and everything on it. So that's what I'm doing here. It says like word break and then the word require, then any amount of white space, an opening parenthesis, any amount of white space, and then wrapped in more parentheses because this is the part that we're interested in. Some quote, a bunch of non-quotes, and another quote. more white space and a closing parenthesis. That's the describes a require with a static string, like it's a little sloppy and it'll match mismatched quotes, but you probably don't have strings with mismatched quotes in your code. So every time we call exec on the regex, it'll find us the next match or null if it's done. So this loop will just basically loop over all the matches to find the actual start of our quote character. We need to take the start of the full match plus the place where the quote actually occurs in that full match, which is what I'm computing here with start. And then these are all collected as objects into an array with the start and the end. So the end is the start plus the length of this actual string. And to get a value out of the string, I'm just crudely calling eval on it, which has problems, but which is a nice way to strip off the quotes. So it's taking quoted string, evaluating it to the actual value of that quoted string. To replace a number of ranges, so the second exercise in a code string, or in any string, the tricky part is that if you replace something with something of a different size, so in this case the integers will usually be smaller than the strings that they're replacing, the whole string after that kind of shifts a little. So the next time you replace, you have to be careful that you're actually still working in the coordinates of the original string. The easiest way to work around that is to sort all these patches in reverse so that you start at the end of the string and you never have to reference any of the string after parts that you already touched. So that's what this does. JavaScript sort is another nice story. By default it sorts by string comparison, but you can pass it a function that returns a number to like customize the way things should be compared, which is what we're doing. We're subtracting the start of the first range from the start of the second one, which gives us a negative number if the second one is before the first, and that causes these to be sorted in reverse order. Then that sorted array we call for each on to iterate over it, and for each range we just use slice and string concatenation to update our code string. And then at the end of the function the updated string is returned. Does that make sense? Okay. Now to build an actual bundler out of that, we're, as the exercise mentioned, we're going to actually support the full resolution algorithm this time, which means that we use the resolve package, which is an npm package that like implements Node's resolution algorithm or calls into Node internals. I'm not sure. In any case, it does what require would normally do under the covers. You give it a string relative to some module, and it finds the module that corresponds to, which might involve reading package.json files to figure out where the main file for a given module lives and stuff like that. It's relatively complicated, but it's hidden inside of this module. So this here is a template string containing this header, this little runtime thingy that we're going to use to actually make require do the right thing. So we updated all the requires, but we need to provide a function that actually implements this like pre-resolved requiring. So this backtick stuff is like template literal ES6 is basically just a string, which can be multiple lines. So for loaded contains the loaded modules as an array again. Since the modules are just a sequence, we can just use an array to store loaded modules. The require function first checks if something is loaded. If it's not loaded, it creates a very simple module object and stores it for later in the cache, and then calls that module corresponding to the number it was given with the module and its own require function. And then at the end it calls require 0, so we have to arrange for the main module to be at position 0 in our list of bundled modules. And yeah, loading a module basically means starting to load the main module. So here's the actual code. Bundle file is called, let me see, yeah, it bundles a single file and calls itself again to go and bundle the dependencies for the other files. No, it doesn't. It has a local recursive function which does the recursing. Because it needs to keep a global list of files so that it doesn't bundle the same file twice. That's what files does here. And code is the actual like code strings for each file. When it needs to add a file, it first checks whether it's already loaded using index of on the cache. If that's not if that's the case, it just returns the ID. So this goes from a path name to a bundle ID, basically, add dep. If it's a new file, we allocate a new ID, so that's like the next position in our list of bundled files, and store the path of this file there. Then we load the text from disk, extract all the dependencies by scanning for require calls. And then we map this list of dependencies, and for each dependency we do a recursive call so that we get an actual ID for that dependency and make sure that all its like transitive dependencies have been bundled. And we create a new object which can be called to, which can be passed to this replacement, this file patching function, using the start and the end of the original string in the code. And instead of the string, the replacement is the ID of this file. So that's what this object here is. And then we have, right, here we call replace ranges. So again, this is using a template literal with string interpolation to create the actual string that will end up in the bundle file containing a function wrapper for the module and then the module code updated to require integers rather than strings. And that's stored in code. And at the end of the function, well, first we like call this inner function once with the start module, so that it'll go through the whole dependency tree, add all the files, and fix up all the code. And then the actual bundle is the header that was defined before. Then all these functions, processed functions, just under each other in the array, plus a few closing brackets at the end of the array, at the end of the argument list. And that's locked to standard out when this file is run. That's the most complicated code we're going to be looking at. Should I go over something again? Does anyone have a question about it? All right. Was there anything else in the... Ah yeah, then finally, to make sure that this all works, the exercise asks you to use an npm module, wire it into your into the app, and rebundle it to see if it works. Let me see for. No. I don't have a ready built version of that, but basically it just shoots little DOM elements every time you answer a question correctly and giving a confetti effect. Right. So then we had 3 competing module systems, but people were kind of converging on CommonJS, and it was kind of clear how to do modules in 2015, and then a new JavaScript standard came out, ECMAScript 2015 or ECMAScript 6, which finally added a module system. And that means we were back again to 4 module systems, and the new one is completely different from what we've been doing before. So universal module loaders won't ever be able to cover that. It has different syntax and a completely different concept of what an export is and what an import does. So one good question is, why did they do this to us? Community uptake has been there. People are moving towards this new module system, but has been slow. Also, implementation has lagged a lot behind. The rest of the standard was implemented by browsers, and therefore also by Node.js pretty quickly. But module support is still behind a flag on every browser, I think, at this point. And Node still isn't there. There's still a lot of fighting happening about how Node should even support it. So that was not really a smooth progression of the community to this new system. I still think it's a useful system. It does some things very differently, as I said, and that kind of helps. So instead of talking about interface values, which the other module systems do, where the stuff that the module exports is just some value, usually an object, maybe a function, and that's all the module loader knows about that. In this case, modules export a set of named bindings instead of a single value. And these are static in that if you look at a file without actually running it, you can determine exactly what it exports and what it imports. And that's nice because now bundlers are no longer living in a fantasy where like, oh, everything is static, but it's actually dynamic. They're actually dealing with static code, which is defined to be static, and they can reason about better. For example, you can now have linters that actually tell you when you're importing something that wasn't exported. You can find unused exports, things like that, which wasn't possible before. The syntax is also quite a bit nicer, especially for exporting, whereas you often had to do like let x equals export.x equals something something because you wanted to use your export locally as well, so you wanted to give it a local name as well as the exported name. Now you can just say export let x equals something, and it's available both locally and globally. Another big difference is that these bindings are like actual bindings. You're not exporting something once and then you're done. If you're later change the value of one of these bindings, all the modules that imported it see the changed value rather than just the thing that happened to be in that slot when they load it. Of course, that also happens if you have an object and you keep reading from that object. But if you did like a destructuring import with CommonJS, where you do like const curly brace name, comma name equals require, that would just pick out these properties from the object once, and then you're stuck with them. Whereas with imports, you're actually creating local bindings, which are like directly linked to the actual binding in the origin module, which is not often useful, but it can be useful, and it makes some things possible, which we'll see in a moment. Who of you has been using ES6 style modules? All right, quite a few. So this basically summarizes the whole syntax. So here I'm first exporting 3 bindings from D. Then there's a special concept of a default export, which is just a binding named default that is exported, but there's some special syntax around that. So if you say import just a name from something, you get the default export. And then there's another syntax for going back to like actually packaging everything up in an object and getting the whole interface as an object whose properties are the bindings. So if you do star as something from a module, you get an object-like thing. Export is just a new keyword that can be put in front of function, class, and variable definitions to actually for export default to create a default export. Some browsers, I think all browsers behind the flag at this point support script as a module. Modules are actually supposed to be parsed differently than normal code, so the implementation has to know ahead of time whether, as they're calling what we have been doing before, that's a script, and a module is a different thing, which is parsed in strict mode by default, and which allows import and export syntax. Oh, shit. Let me see. Does this work better? Okay, let's try. Problem with script type module is that there is nothing defined about actually resolving these, except initially the page, and inside of a script, if you do import but you can't do import jQuery or something, which makes this amazingly useless for a real-world project. You still have to put in some pre-processing. You have to expose the whole directory tree that these are part of. So I'm not aware of anyone actually using these to do like, as I said, I'm not aware of any. I was hoping to be able to use this to like cut out the compilation step again, because I really like developing directly against the source code without having some process in between where sometimes it crashes and then I'm looking at the old code without realizing it and I'm just wasting time. But script type equals module is not that yet. There are plans to add a standard that allows you to define resolvers for your modules, at which point you could try this again, but for now we're stuck with build processes, which isn't that bad because the community seems to have moved on to using experimental syntax features, using just completely non-standard extensions like JSX or type checkers like Flow or TypeScript. For big projects, very few people are actually writing vanilla JavaScript that runs directly anymore. So it seems that build tools have won, and we should all just accept that we're going to have to use build tools. Speaking of build tools, one really cool thing you can do with ES modules is a style of bundling which was pioneered by the tool called Rollup, which just basically collapses all the module-related boilerplate and makes it vanish from your output. And this was not possible with CommonJS or AMD-style modules, but like there's some very clever programming language people working on the JavaScript standard, and they try to define things to make things static enough that you can do clever things like this. So here you have two modules. The first one exports a single binding, and the second one imports it and then uses it. And if you run rollup over these two, you just get the binding defined and the use of it without any trace of different scopes or different like import-export mechanisms. It's all gone. It can do this because bindings and variables are pretty much static in JavaScript. There's exceptions like local eval and the with statement, but no one uses those anymore. So we can just treat JavaScript scopes as something that's static, that can be determined by a tool exactly which variable refers to which definition of that variable, which makes it possible to do things like renaming variables, which almost all minifiers do, for example. So even in this case, if the second file were to do import x as y and then console.log y, it could still see, okay, this is the same binding. I'm just going to rename that use of y to refer to x. Or if there's another module which has another local variable called x, they'll all end up in the same scope, but you can just rename variables that happen to clash in order to still produce a bundle with a single coherent scope in which this might be hundreds of different modules. As long as they're defined in this way, they can all peacefully coexist in one scope in your output bundle, which saves a lot of space. Someone also runtime overhead. Someone did like some benchmarks, I think last year. Nolan Lawson wrote a blog post about the cost of modules. If you have like a classical Browserify style bundle where everything is wrapped in its own local function scope and all the requires and imports are still there, there's just a ton of file size being wasted if your modules are small enough, and typical modern projects use really small modules because they're all still there. They all still have a function wrapper and they all communicate to each other with require. And there's also just a lot of overhead from going through these require calls and these interactions created by like reading properties from objects instead of directly having access to the bindings. And this just eliminates this. So because the ecosystem isn't at a point yet where everyone is writing ES modules, you probably can't use this when you're writing an app yet. But if you're distributing a library, it's really recommended nowadays to write your library as a bunch of small ES modules and then use Rollup to create one big distribution file from that, because it removes all this overhead in your own build step, and other people don't even have to know that you wrote this as small modules. They just consume your single big module as a dependency. So as I said, Node isn't really there yet in terms of implementing ES modules. There are shims. I think the best one at the moment is called Rayify, which is a thing that you load. You require Rayify once, and from that point you can just interchangeably use ES modules and CommonJS modules. It registers a hook with Node.js to be like a preloader, and it translates your modules to from ES modules to the corresponding CommonJS code, which I think still fails in some really obscure corner cases, but you can kind of emulate the semantics of ES modules by inserting a bunch of boilerplate code. So then you can run ES modules in Node, but this is awkward because you have to first load the shim. It adds a bunch of overhead and magic to loading. So this is good for running tests and stuff like that, but for production code, you probably want to first preprocess your code and then load it into Node. The plan for Node is to do something where, because as I said, these are parsed differently, old school scripts and ES modules, is to require ES modules to be called .mjs instead of .js. Module.js. JSM was already used for something else, as I understand it. And that way, you can still use them interchangeably. If you require something which happens to be a module, it'll be treated as a module. If you import something which is actually a CommonJS module, then it'll be just silently made to behave like an ES module. It's a bit complex and tricky, but it's probably at least a way forward so that the ecosystem can continue moving in the direction of a single module system. So I do think these are the future, and that hopefully in 5 years we'll all just be constantly using this. But it's going to be a long way because the whole ecosystem is now kind of on CommonJS modules. The tools are not there yet at all. It's going to take a while, and there'll probably always be CommonJS modules on NPM because a lot of these modules are never going to be updated again. So again, this is another piece of historical baggage that we as a community have now accrued and are going to have to deal with for the rest of our lives, or at least until we move on to another language. So yeah, as I said, you're probably going to have to get used to using some kind of tool chain to check, translate, bundle, minify, and probably even like watch or hot reload your code as you're developing it. There's like, please don't manually run your build step every time you make a change and before you test, because that's terrible and you're going to forget it or get a... most tools support a feature called watching, which is file systems on modern platforms allow processes to register like an event handler saying if this file changes, please notify me. And many JavaScript tools support this, where they already know what files they read, and then they register these handlers and just keep on running. And every time you save, they'll just rebuild your thing very cleverly, incrementally, if it's a good tool, so that it only takes a few milliseconds to rebuild, and you don't have to think about, oh, did I rebuild yet? Which version am I looking at? You still, I mean, I know Rollup sometimes crashes if you set it to watch, and then you're refreshing the page and wondering why things are still broken, and then you look at your Rollup process and it crashed. Stuff like that still happens. There is definitely a cost to more tooling and more complexity, but we'll have to deal with that. Another thing is that if you're running code that's not actually the code you wrote, debugging gets a little bit awkward. So stack traces point at your bundle instead of your actual code, and then you have to figure out what that line in your bundle actually is. There's a feature in browsers, and there's also support for Node if you load another hacky shim, which is called source maps, where you provide the browser with an additional data structure about your bundle, telling it which part in this bundle came from which file, which line, and so on. So there's a special command syntax where you can say, I think, // hash, and then point at a file that contains some other obscure data structure which describes, which is created by your build tool. So almost all build tools support this. Rollup, Browserify, Webpack. You can tell them to output a source map, and if you do that, you usually just don't have to worry about it. Your stack traces will point at the code you wrote rather than the code you bundled, which is really great. It's amazing how quickly that was implemented and how quickly all the tools adjusted to that. So then for the next round of exercises, we're going to bundle some ES code using Rollup. So there's a 2015 directory which has Rollup pre-installed under Node modules. And it's asking you to check out the README for Rollup if you're not already comfortable with it, or just run Rollup with --help and figure out how to go from a bunch of separate modules to a bundle, how to load that into the actual app, and then there's some more advanced questions building up from that. I'll take, yeah, we have some time left. I'll take 10 minutes for this one, and again, don't hesitate to talk to me. All right, let's continue. So Rollup, like most bundlers, takes its main input file as a command line argument, and then you can, by default, it'll just spit out the bundle to standard output, but you can tell it to use something else. So here in this invocation, I'm just saying -o bundle.js, so it'll find all dependencies of app.js and put them in bundle.js. And if you look at the code, it's actually like my trivial example of on the slides. It's very clean, simple code. Even the variable names even usually make sense because it just takes, if it doesn't have to rename it, it just takes the variable as you declared it. By default, it'll just create a plain flat file. You can say -f IIFE for immediately invoked function expression to wrap it in a function, which is usually a good idea if you're going to be running this in the browser. And that's all it takes. This is like a nice and elegant and simple app. We'll get to Webpack later, which is a very powerful but not so elegant and simple app. I'm a big fan of Rollup, but as I said, it's not always useful for big projects. Then if you create some bug intentionally in the code and look at the backtrace in the browser, it's just pointing into your bundle, and you probably don't want to do that during debugging, so you can say -m bundle.js.map. People usually just say .js.map for these source map files, and then it'll output two files, bundle.js and bundle.js.map. And at the end of bundle.js will be a little command pointing at the source map. Alternatively, you can say -m inline to put the source map inline, which will create a much bigger file. But you can, like, if you're going to move it around and put it in some other directory, it can be easier to have it inline rather than having to move two files around. But for production, that's a really bad idea because it adds a lot of cruft. Like all the source code of the original files, along with this mapping data structure saying which piece of data corresponds to which piece of the bundle file. So that's too much data to be shipping to your users in production, which is why separate map files exist. But yeah, at this point, your backtrace will, on any halfway modern browser, show the actual source files rather than the bundle file. Then to get automatically rebuilds set up, you just add the -w command line argument. The tool will not exit when you run it. It'll just keep on running until you abort it, and it'll just watch all the input files, which it knows because it's like it found them when it scanned for dependencies, and do a quick rebuild. Like I got 20 milliseconds for a rebuild when I changed something. Of course, if your project is bigger, this will be a bit bigger, but it's quick because it doesn't have to do all the work again. It's like clever about keeping the stuff that didn't change around and only updating the parts that you actually changed. Then I had a question about what a bundling algorithm like this could look like. So this, we're not going to actually implement this in code, but roughly it talks about bindings. So it creates for each file a set of top-level bindings, along with information about whether these were imported from somewhere and whether these are exported. And it just, like all our tools have been doing so far, it just continues scanning dependencies as it finds them, and creating bindings for those. And then it goes to work merging these bindings. So if a binding is imported from somewhere, it scans, it finds the binding that's actually the export that this binding corresponds to, and it says, like, these are the same. And it uses these like merged bindings. Some of them don't need to be merged. If they're just a local top-level variable, they remain like just a plain binding. But as it accumulates these, it can check, is there already something by this name in existence? And if that happens, it has to like take the source file in which this is referred to by the conflicting name and rename it throughout the source file. But that again is a problem that has been solved. And in the end, you have you have all the bindings with unique names, and the ones that refer to the actual same thing are merged, because that can be done statically, and you can just dump the renamed code into one big file and it'll work mostly. For things like export default, you have to be slightly clever to actually assign a name to that and create a const statement or a let statement that binds it. But on the whole, this is not a hugely complicated thing to do. For syntax like import star s something something, you need to generate some more boilerplate. Like you create an actual object in the output code, which has all the bindings exported by the module that is treated as an object, and then you have to set things up so that these actually stay current, so that when these bindings are changed, the object is changed. So at that point, if it's a mutated binding, which you can also determine statically, by inspecting the source, you can see whether a given variable is ever assigned to. So for some things, you can just optimize this away because they're never mutated. But if they're mutated, then all the mutation and the reading has to go through this object, so that even if the binding is changed at runtime, everyone is still seeing the actual same binding. Okay, moving on. Now, if you have both a working module system and a repository with modules, and incurring dependencies becomes practical, that's the point where the ecosystem actually starts to use dependencies everywhere, which is what the various complaints about node modules directories becoming too big are about. It's like, the system is working, we can use dependencies, and they actually arrive. Of course, if you're shipping on the browser, you still have to be a bit careful about what you're going to end up pushing to the client. We'll come back to that in a moment. But one thing about libraries is that they're not published once and then stay the same forever. They evolve, they're improved, they're extended, sometimes they're completely rewritten. But when you're depending on them, you're writing code against a specific form of that library, which is what version numbers were invented for. NPM mandates that modules use semantic versioning, which is a specification of one way to do software versioning. Namely, each version gets 3 numbers separated by dots, called a major version, a minor version, and a patch version. And there are strict rules about what may be different in different versions of the library based on which of these numbers are changed. If you have 2 versions that only differ by patch, they're required to have the exact same interface. Like any code written against the old one should work with the new one. If you increase the minor version, then you're saying I'm only adding functionality but not removing any. So existing code should continue to work, but code written against the new version may not work against the old version. If you're changing the major version, then everything, all bets are off basically. You're making a breaking change and old code might continue, might stop working. This is of course not observed all that strictly by everyone all the time, so you'll often see packages on NPM violate this, and even if it's observed perfectly, it doesn't solve all our problems, because you might introduce a new bug in your patch version and it'll still break code that depends on your thing, or you might fix a bug that someone was actually depending on the behavior that you consider a bug. So dependencies are still hard, even with semantic versioning, but it's definitely a big improvement compared to everyone just doing whatever they want. So I encourage you to, like, if you publish something on NPM, to really try to be serious about how you version it, which is hard because we often think about versions in different ways. Like version 1.0 is considered a major milestone where you are maybe like declaring the library production ready. And then 2 weeks after that, you find some issue that's going to require a breaking change. And now you have to bump your major version to 2, but you don't really want to yet because then you felt like it still was 1. And but people are coming around to this and just treating the version as a stupid number that doesn't mean anything beyond what Semver ascribes to it. So the easiest thing now would be just to figure out one version of a dependency that your code works with, and then say, okay, this is the version I depend on and never change it again. That's also not optimal because there are often going to be vulnerability fixes to code or just really big performance improvements or other improvements. And if you stay stuck on a version, you're never going to get those, which is especially nice with vulnerabilities because people are actually actively working to exploit those. And it's happened quite often that even like months and months after some library patched some issue, people were still getting exploited through old versions of this library that they had installed because they just weren't upgrading. Which is why NPM allows you to specify a version range rather than a specific version that you depend on. Usually, the clever thing is to just say anything that has a minor or patch version higher than this given version is okay with me. The notation for that in NPM system is caret and then the version. So caret 4.3.2 means that 4.2.0 is not okay, but 4.5. something or 4.3.6 is okay as long as like it's not below the version you gave and its major version is exactly the version you gave. That matches, which means that exactly what semantic versioning describes should still work, should still be compatible, is matched by your range. And there's another reason to use version ranges, namely that many dependency trees contain diamonds, or rather like things that join back again on each other. For example, a library like Lodash or React or whatever is likely to be required by a whole bunch of modules that you depend on if you depend on more than a trivial amount of modules. And if these specify like 2 versions, if these can be reconciled, if they're like ranges that overlap, then NPM can just find a version that satisfies all of the packages and install that. But if they don't, as in this case, where one module is asking for version 1.x and the other is asking for version 2.x, that breaks apart in some module systems, which don't allow multiple versions of a single library to be loaded, which is a surprising amount of them if you look at other languages. Then you're just dead at this point. It's usually called dependency hell, and it means that a given dependency tree cannot be installed. Fortunately, NPM is better than that. It allows multiple versions to be installed. It's using Node's resolution mechanism for this. If your library has its own Node modules directory with its own dependencies installed, then if it requires a given library, Node will take the one from there, and the bundlers use the same algorithm, so they also get like multiple versions of a library in your bundle, which is not always ideal. We'll get back to that in a moment, but at least you can install a dependency tree that contains conflicts like this. Initially, NPM would always duplicate dependencies. If you like, basically your dependency, your Node modules directory structure would mirror the package.json files. So each library would always get its dependencies installed under it, and that library would get its dependencies installed under it, and so on. Which really broke down once people started to, like, for example, Babel was written as a whole bunch of different modules which all depended on each other, and if you installed it with npm2. npm3 started moving away from this strategy, but if you installed this with npm2, it would create a gigantic fractal dependency tree, and it would be really slow to load, and it would load several packages like 10, 20 times, which is also tricky. Like, you can load a package multiple times, but if the module has its own state, for example, and you put some state in one instance of the module and then expect it to be present in another one, it's not there because they're just completely separately loaded pieces of code. Also, if you do instance of, the instance of operator, just you give it a constructor and it checks whether an object is an instance of that specific constructor. And if there's like 10 versions of that constructor floating around your system, it's often going to fail because this object happened to be an instance of another copy of that constructor. So that's bad. We want to avoid duplicating dependencies, but it's good to have that fallback if there really is like a hard conflict. So since npm3, it's very best if you install a system to install all the dependencies on a flat layer in your direct node modules directory, and only if it has some conflict, then it'll like create another layer in this tree where it installs another version of a given module, which can still go wrong, because at that point, if you have like a conflicting package that exists often, then it'll be duplicated a bunch of time under the separate libraries that require it. Dependency management is really hard, and I think NodeTool gets this completely right. Yarn has some improvements here, but still you can shoot yourself in the foot, and it's tricky to once you have a lot of packages sharing a given dependency, it can get tricky. Another thing that comes up with managing your installed dependencies is reproducing a build. Say you have your super important production system is depending on library X, and you say, okay, version 5.2.1 and up is okay, and you run your tests, and it installs version 5.2.3 because that's the current version on npm, and the tests all pass, so you say, okay, put it in production. And at that moment, the maintainer of X publishes 5.3.0, which introduces a new bug, and your production ends up installing that one because it went to npm to figure out what the recent version is, and everything breaks, and your users are really unhappy, and you did everything right. Like, you tested before you deployed, but you're still breaking your build. To work around that, npm still contains a feature called shrink wrap, where you resolve your dependencies once, create a file that lists them, and then you put this file into your repository and deploy that along with your system, so that you have like an exact fixed set of dependencies that you want installed, and you tested those exact dependencies, and you get those installed in production, and that means you'll at least have the same code running there. Yarn, the other like client-side tool for working with the npm registry, started doing this by default from when it was published, and npm 5 and up also do this by default now. They use a file called packagelog.json, so you have kind of like a data flow like this. Your package.json is resolved, computing a packagelog.json, which includes a hash of package.json so that the tool can see when it's out of date. And then your packagelog.json is the actual source being used to generate your nodes modules. So you have an extra step in between, which allows you to get more control. And the idea is to commit packagelog.json to your repository, so that your actual repository changed when your set of recommended dependencies change. This is not important when you're maintaining a library, but when you're maintaining an actual app, you probably want to work with a package log file. So I touched on the problem of if you happily incur dependencies, your bundle is going to get huge before. So that's if you're writing a web app, you don't want to ship 5 megabytes of JavaScript to every user as soon as they land on your page, because downloading is slow. Downloading that over a mobile connection is extremely slow. Parsing and running all that is expensive. It's going to waste a bunch of battery for mobile devices. It's just bad. So that's why I think Webpack was the first tool that did it really well, though the other tools also usually support something like that. Browserify definitely does. It's called code splitting, where you don't create one big bundle, but create a bunch of bundles, and then either explicitly or automatically load, like your like base app is in your main bundle, and that's loaded when the user lands on the app. And then when certain things happen that require more code, you start loading more bundles, and that way you like only load the code that you actually need, and the amount of wasted bandwidth is kept under control. The recommended way to do that with Webpack nowadays, if it didn't change in the past 7 days, is to use dynamic imports, where you Webpack also supports ES modules, also does some of the cleverness that Rollup does to a certain degree. If you do a normal import, that means that binding has to be present when the file is first run, so that means it's part of the main bundle. There's a not quite finished proposal to the JavaScript spec to have another import syntax, looking like the second line there, which is import as a function call, which produces a promise, which actually is going to load that module at runtime, and then when it's loaded, resolve the promise so that you can actually start using it. So that's what this line here does. It waits for Y to asynchronously load, and then it starts using it. The thing that this promise resolves to is the interface object, comparable to what you would get if you import star from something. So it's an object containing the bindings as properties. And Webpack, so no actual engine supports this syntax yet, but Webpack does. And what it does at that point is like it stops, oh, it's loud again. It stops statically bundling at that point, but creates another bundle for all the stuff that's like after the dynamic import. And when this import is actually run at runtime, it starts loading that, and when that bundle is loaded, it resolves the promise, and you can continue running. And of course, it caches that stuff so that if you run it multiple times, it only gets loaded once. And that's a way to load things on demand. So if you say you want to include some data visualization using D3, which is a really cool library for data visualization, but it's also huge, and you probably don't have it on your landing page. So you have the code that is run when this actual data visualization is called for. Dynamically import D3, and then do what it needs to do. Then you'll get two bundles, one for the landing page and one that's only loaded when this code is run. That depends on D3. The last set of exercises are about using Webpack, including code splitting. So it again has this DOM confetti thing. I think it's ready to run this time. Oh no, I have to go to solutions probably. I didn't build it yet. So yeah, follow the README again. It'll go through a few steps of using Webpack to again bundle this ridiculous app of ours, and try to look into some of the things Webpack is doing under the hood. So I hope you all saw the dumb confetti effect now, which I think is really adds a lot to this app. Like you can just get confetti when you. It also screws up the scroll bars because CSS. The solutions. First, to split this, all you have to do is remove the static import and replace it with a dynamic one. In this case, that looks like this here. So you import DOM confetti. This expression results in a promise. So to wait for that, we call then, and after that resolved, we get an interface object. So we have to add .confetti after it again because that's the actual function we want to call. And because this is just a silly little interface thingy, it doesn't really matter if the load fails. In production code, you might want to actually catch a failure on this promise and tell the user, oh, sorry, we couldn't load the app properly. But yeah, just making this change to your code and rerunning Webpack will just magically give you a split bundle. You can check in the development tools that it is in fact loading another file when you enter a correct answer. So that's pretty magical and pretty nice. Of course, people are taking this further. Another problem with modularity is CSS. Lots of modules will depend on their own piece of CSS, and somehow getting that all loaded when loading an app is very awkward if you're using explicit link text pointing to CSS files. So why not require CSS files or import CSS files? That's what a bunch of Webpack plugins allow. I never really understood why there's two plugins for that and exactly how they interact, but the magic invocation that you get from the docs is this. You add, for files that end in .css, you add two loaders, style loader and CSS loader, which will take that CSS, wrap it in your bundle, and add a bunch of magic around it, which injects the CSS into the page when the bundle is loaded. So at that point, you no longer have to worry about arranging the correct link tags and making sure all these separate CSS files are loaded. They're part of your bundle, and when your bundle is loaded, they're available. Then there's this really neat plugin called Bundle Analyzer, which gives you a graphic like this. Well, it's not that visible on the screen here. Let me zoom out a bit. Oh, it adjusts its own size when I zoom, so I can't zoom out. But this kind of shows a graph of the things that are part of your bundle by size. So the surface area of all these little rectangles corresponds to the code size they take up in your bundle, so you can quickly see how am I wasting my user's bandwidth. In this case, we are wasting our user's bandwidth with add styles and URLs and style loader, which apparently are part of this CSS plugin. So for a small app like this, it may be a good idea to load the CSS the old-fashioned way, because here I think at least half of the bundle is the whatever the hell this plugin is doing to load the CSS and inject it into the page. But using this tool, so again, the plugin is called Webpack Bundle Analyzer, and it's when you run Webpack with this plugin enabled, it'll open a browser tab showing you this graph. Which can be helpful because it's a really magical process, and just reading the files that are output is often not very enlightening because they're huge. A very hard problem that comes up with code splitting is that if you have, say, 3 parts, your main bundle and 2 other bundles, where does the code that both these other bundles depend on go? You could duplicate it in both bundles, but then you're again loading more code than you need to. You could create a separate bundle, but then if you do enough splitting at some point, that separate bundle will be huge and you'll still not reap a lot of benefits. There's a plugin called Commons Chunk plugin, which kind of does this strategy of creating an extra bundle with all the shared code for all your like split off bundles in it. And it allows a bunch of configuration options to like handhold it into which should go into a separate bundle. Maybe you have one big library that you just want to be a separate bundle so that it's not pulled in unless it's needed. You can specify that, and then Webpack will set up things so that it's loaded at the right point automatically. At some point, configuring Webpack gets more difficult than one of these simple bundles that we wrote from scratch ourselves, but it does a lot. And as I said, for like serious apps, it's currently the best way to bundle your code, I think. If you need code splitting and interacting with all kinds of legacy module systems, it does that really well at the expense of being really complicated. That's all I have. As I said, this link here is the repository of this. So if you feel like looking at a solution again, the solutions are all in the repository, and you can study them if you feel so inclined. Thank you for listening, and the lunch will be starting in 5 minutes, so I think the timing is all right. Thank you.